So I have done things a little different. If you've watched the previous reviews or came to the previous reviews, I didn't have everything nicely split up. I just kind of hand wrote it. This time I came prepared, so I've put everything onto its own page, which will hopefully speed up the process a little bit and hopefully not be hours long like the previous ones have been. So I'm hoping this one will go a little bit quicker. So I'm, of course, always happy to answer any questions that you have that are outside of this review, but my main plan is to go through just the review questions. If you have questions at any point in time that you want me to do that are not these ones, I'm happy to do them. Just let me know. I have the chat box open on my computer so I can see everything people are typing, just like in class. All right, then we'll go ahead and get started. So for this first problem, find the absolute extrema. So you're finding absolute extrema on an interval, which means you're going to find all the critical values, and then you're going to throw out the critical values that are not within the interval and plug all of the critical values plus the endpoints back into the original equation. So taking the derivative, we got 6x squared minus 6x minus 12, setting it equal to 0. We can factor out a 6. This factors into x minus 2 times x plus 1. You get the critical values 2 and negative 1. Now, negative 1 is not within the interval because the interval is 0 to 3. So we don't want to look at that one. Then we're taking these values and plugging them back into this original function. So this value here, 0 and 3, we get plugged back into this original. So f of 0, if you plug 0 in, you're going to get 0 cubed, 0, 0. It's going to be 1. If you plug in 2, 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 1. Let's see, so 2 to the 4th minus 12 minus 24 plus 1. We have negative 19. And then f of 3, 2 times 3 cubed minus 3 times 3 squared minus 12 times 3 plus 1. I'm getting negative 8. So the smallest one of these will be our absolute min. The biggest one will be our absolute max. So our smallest one here is this guy. So we have a minimum at, and this is the coordinate point 0, or not 0, the minimum's at 2. Min's at 2, negative 19. And then the max is at 0, 1. Any questions on part A? If not, I will just keep on going. Oh, so somebody said in the chat, like, I never made sure they were in the domain. That's the important part. If you're on an interval, you have to make sure they're within the interval. So the only time you're really worried about this, again, is when you have an interval that you're given. Other than that, you don't, like, if you're looking for just the local extrema, that way you don't have to worry about the endpoints or making sure the critical values are within there. All right, so for this next one, taking the derivative, we have 2x minus 8 times 1 over x. I'm going to write this as 8 over x, setting it equal to 0. Making a common denominator here, we'd be multiplying by, let's see, let me erase. Oops. You'd be multiplying by x over x here to make a common denominator. So you'd have 2x squared minus 8 over x equal to 0. Factor out of 2, we have x squared minus 4 over x equal to 0. X plus 2, x minus 2, all over x equal to 0. So here we have x equal to negative 2, x equal to 2, and x equal to 0. Because you want, with those critical values, you want to check places where it's undefined as well. You might have domain issues because it might be undefined in the original function. But because we're on an interval here, that's not going to be an issue. We already have an interval. In a problem where it was looking for local maxes or mins, you'd want to double check that your critical values were within, well, your important values rather, your important values are within the domain of the original function. So in the interval 1 to 5, we would throw out not him. We throw out him because he's not in 1 to 5, and we throw out him. These would get thrown away anyway because they don't work in the original function. And then we'll put in the endpoints and x equals 2 and see what we get. So we have 1 squared minus 8 ln of 1. Ln of 1 is 0, so this just comes out to be 1. F of 2 will be 2 squared minus 8 ln of 2. If you plug this in your calculator, you should get, I think it's negative 1.55. And then plugging in 5. This should give you, and I probably should put, these should probably be approximates because they are approximations. I'm rounding the number. 12.12. So this right here is our minimum. This one here is our maximum. Now, normally we're giving exact answers here. So our minimum, we would say, was at 2 comma, I'm going to write this as 4 minus ln, 8 times ln2 to give the exact answer there. And there's a max at 5 comma 25 minus 8 ln 5. Once again, just to give our exact answer instead of our approximated answer. On a test, unless otherwise noted, the answer should be in its exact form. Any questions on part B? I'm going to move on to part C. Keep us moving here. Same idea here. We're going to take the derivative. Now this is a product rule problem, right? So this is product rule. So it's going to be f prime g, so 2x e to the x, plus g prime f, which I'm going to write as x squared e to the x. I can factor out an x and an e to the x here. So I can factor out an x and an e to the x. I'm left with 2 plus x equal to 0. There's actually 3 chunks here that you have to set equal to 0. So you'll have x equal to 0, e to the x equal to 0. Now, if e to the x is equal to 0, you would take the natural log of both sides. Technically, that's how you solve exponential equations. But then you'd get that x is equal to ln of 0, which is undefined. I've mentioned this before, but e to the x will never equal 0. So you don't get anything important out of that one. And then here we have x equal to -2. Both 0 and -2 are within our interval, so we're going to plug in both of these values and the endpoints. So f of -3, that would be -3 squared, e to the -3. Right, and this one, I'm coming out to be around 0.45-ish. We're rounding these just to get an idea of where they are, because I can't look at the number 9 e to the -3 and know what number that is. I can't determine whether that's bigger or smaller than another number very easily. So we do the rounding, not because it's part of our answer, but to choose which one of our answers, what actually our answer is going to be. So let's do -2. So -2 squared, e to the -2. 0.54. This one's nice and easy, right? 0 squared, e to the 0. This is just 0. And finally, f of 1. This is 1 squared e to the 1. So that's literally just e, which is it's approximately 2.72. This guy here is the smallest. So he's our minimum, is what I want to write there. This guy is our biggest. He is our maximum. So we have a min at 0, 0, and a max at 1, e. And that is part C of this problem. Moving on to part D. There's a little fly flying around and I want to... It's flying too fast for me. That's okay. All right. F prime of x once again. 1 minus, now this will be 2, and then cosine's derivative, remember, is negative sign. So this is really 1 plus 2 sine x, setting that equal to 0. You'll get sine x is equal to -1/2. We are on the interval -pi to pi. So using your knowledge of the unit circle, -pi, oops, that's not what I meant to write. That's not what I meant to write. So this is pi, but this is also -pi. All right, because pi is this amount and -pi is back here. So this is 2 pi, it's just that it goes from -pi to pi. So really, it kind of looks like this. It starts here and then goes all the way around. Both of these angles are going to be down here because sine is the y value and y is negative in these regions. So you're looking for these values right here, which are going to be in that -pi to 0 range. You just need to figure out which angles those are. Those angles do end up being the -pi/6 angles. So 1/2, let's see, yeah. So this guy right here is -pi/6, -5pi/6. Once again, this is trigonometry, so it's back from your 127 class, so you might need to review those 127 notes. But these are the times where the y value is -1/2. So you get x equal to negative 5 pi over 6 and negative pi over 6. Right? We've already verified that those are within this interval because we chose them based on being in this interval. An option you would have, if you wanted to just do this with if you wanted to do it with 0 to 2 pi instead, you still know that these guys are down here. Normally you would say that this angle is 7 pi over 6 and that this angle here was 11 pi over 6. And you could subtract 2 pi off of these. And you would get negative 5 pi over 6 because these are coterminal angles. You can add or subtract 2 pi to get coterminal angles. And that would give you negative pi over 6. So that's another way of getting those same angles. Plugging them all back in to this equation up here, including these endpoints. So we have f of negative pi, which is going to be negative pi minus 2 cosine of negative pi. Negative pi is back here. Cosine is the x value. So the x value here is negative 1. So negative pi minus 2 times negative 1. Negative pi plus 2, which is approximately negative 1.14. Next, plugging in negative pi over 6. So we have negative pi over 6 minus 2 cosine of negative pi over 6. That's going to be negative pi over 6. Let's see, cosine of negative pi over 6, that's going to be positive root 3 over 2. Yeah. So 2 times root 3 over 2, which is the same thing as just root 3. So negative pi over 6 minus root 3. Can you not, Archie? I'd appreciate it if you just didn't. Dogs. Right? That's going to give you negative 2.26, approximately. Negative 5 pi over 6. That's going to give you negative 5 pi over 6 minus 2 times, this is going to be negative root 3 over 2. So this is going to end up being plus root 3. Let me grab that number real quick because I don't have that number offhand. Approximately negative 0.89. And then finally, almost there, the last endpoint, pi minus 2 cosine pi. So that's pi minus cosine of pi we already said was negative 1. So pi plus 2, which is approximately, I believe, 5.14. Oof. So digging back in that trig is the important part here. This guy down here is our max. This guy, is that our, no. This guy is our min. So we have a max at pi, comma, pi plus 2 is the exact value. And we have a min at negative pi over 6, comma, negative pi over 6 minus root 3. So I know that was a slightly more tricky one, but are there any questions on that one? Move on to part 2, or not part 2, moving on to 2 in general. So this one says find the x coordinates of all local extrema and find the intervals of increase/decrease. So we don't have to actually find the coordinate point for this one, just the x coordinate. And then we need to declare whether it's a max or a min and do the increasing decreasing thing. So for these problems, you're finding the first derivative, finding the critical values, making a sign chart. So y prime is 3x squared minus 1. Setting that equal to 0, you get 3x squared is equal to 1, x squared is equal to 1/3. So x is equal to, important here, plus or minus the square root of 1/3. If you're doing the square root property, you need to remember that, plus or minus. So this will be negative square root of 1/3. This will be positive square root of 1/3. You'll want to put that in your calculator so you know what test points to take. So this is approximately negative 0.6. This is approximately positive 0.6. So when you're taking test values, you could use -1, you can use 0, and you can use 1. But it's important here that you know that like this number, I mean, what is the likelihood you would have chosen -0.5 for your test value? Not very likely, but you want to make sure you know where these values are before you choose your test points, because you want to make sure they are in the right interval. You're plugging back into this guy here, right? Your derivative. Now, normally they're factored, so it's a little bit easier. Here you just kind of have to do the math a little bit. -3 squared minus 1, 3 times -1 squared minus 1, that's going to be 2, which is positive. Plugging in 0, 3 times 0 squared minus 1 is -1, which is negative. 3 times 1 squared minus 1, that's 2, which is positive. So we have increasing, decreasing, increasing. You can kind of draw a little picture in here. So you have a max here and a min here. So there's a max at x equals negative square root of 1/3. There's a min at x equals positive square root of 1/3. The function is increasing from -infinity to negative square root of 1/3, and also increasing from square root of 1/3 to infinity. And it's decreasing on negative square root of 1/3 to square root of 1/3. So the numbers, they're kind of nasty here, but they're doable. And I want you to keep that in mind when you go to do the test, that even if numbers are on the nastier side, that's okay. All right. Moving on to part B. Once again, it's the same question. It's the increasing, decreasing, local max, local min. So we'll take that derivative. This will be 8x cubed minus 8x. Set it equal to 0. We can factor out an 8x, and you're going to have an x squared minus 1. That's an x plus 1, x minus 1. So you'll have x equal to 0, x equal to -1, and x equal to +1. Same idea, making a sign chart. And you do need to show this work. This is important that you show this work. So you have -1, 0, and 1. I'm going to choose -2. You don't have much of a choice here. -0.5 is probably the easiest. Same thing here. +0.5 is probably the easiest. And 2. And this one, because we were able to factor it, we can just plug them into each of the factors here and do the positive negative thing. So -2 itself is negative, -2 plus 1 is negative, -2 minus 1 is negative, 3 negatives make a negative. -0.5 times 8 is negative, -0.5 plus 1 is positive, Negative 0.5 minus 1 is negative. Two negatives make a positive. 0.5 is times 8 is positive. 0.5 plus 1 is positive. 0.5 minus 1 is negative. And then 8 times 2 is positive. 2 plus 1 is positive. 2 minus 1 is positive. 3 positives make a positive. So decreasing, increasing, decreasing, increasing. And so you can see we have two minimums and one maximum. These are just local, not absolute. This question asked for local. So I'm going to say there's a min at, and it just wanted the x values, so negative 1 and 1. There's a max at 0. The function is increasing from negative 1 to 0, and it's also increasing from 1 to infinity. And it is decreasing from negative infinity to negative 1 and 0 to 1. And that's that for this problem. This one pretty quickly. Once again, if you have any questions, I know I'm kind of going through it a little fast. I just want to make sure we get through all the problems. And I know there are 14 problems and a lot of them have multiple parts. So I'm just going fast. But if you have questions, feel free to type them, even if I'm not on that problem currently, because I can always go back to that problem. All right, once again, for part C, we're doing the same thing here. We're going to need to take a derivative. This is a product rule problem. So we have f and we have g, and we'll have to do product rule. So f prime is going to be 1. So this is e, and then 1 over x is the same thing as x to the negative 1. I am going to write it like that because I'm going to need to do power rule here. And, chain rule and power rule. So that's not x minus 1. That's x raised to the negative 1. Just to be clear, it's x raised, not x minus 1. X raised to the negative 1. There's that fly. Dang it. All right. So with e, it's the derivative of the exponent. So the derivative of x to the negative 1 is negative x to the negative 2. And then you leave the e part alone. Rewriting this a little bit. So there's going to be a negative. There's going to be an e. And then you can rewrite this as 1 over x if you want to. And then the x to the negative 2 just means an x squared in the denominator. I'm rewriting it like this because I know I'm going to have to convert it into one fraction eventually. So it makes sense to rewrite it in its fraction form. So this is f prime g, so that's e. And then, once again, if you want to rewrite it as 1 over x, you can do that at this point. E raised to the 1 over x plus g prime, so negative e to the 1 over x squared, g prime times f. Here, one of these x's is going to cancel, so this one of those x's will cancel. We have e to the 1 over x minus e to the 1 over x, setting this equal to 0. We want to make a common denominator here, so we can make it one fraction. So that common denominator is going to be x. So we have x e to the 1 over x minus e to the 1 over x, all over x is equal to 0. We can factor an e to the 1 over x out, and you're left with x minus 1. So e, we already said that this will never equal 0, so we don't have to worry about him. Here we get x equals 1, and here we get x equals 0. Now here's where you have to be a little tiny bit careful. You have to be a little tiny bit careful. It's okay to make your denominator of your derivative undefined, as long as it's defined in the original equation. However, if we look at the original equation, there's one issue we have to worry about. E itself has a domain of everything, but because its exponent has 1 over x, we can't have x be 0, because if x were 0, you'd end up with 0 e to the 1 over 0, and while that looks like it works, it doesn't quite work, because you have that 1 over 0 that you can't have going on. So x cannot equal 0. So it's important that we include this on our sign chart, because we can change from increasing to decreasing there, but we can't have a max or a min at x equals 0. But it does go on the sign chart. It essentially becomes an important value, but not a critical value. So what I like to do, I'm just going to put like asymptote lines, just to note that it's not possible for that one to be a maximum or a minimum. E itself, this guy right here, is always going to be positive. I can put this positive here for all of them, because its exponent changing won't change whether E is positive or negative. It just changes whether E is essentially in the numerator or denominator. Plugging -1 in, then I'm just going to plug them into the other two now. -1 minus 1 is negative. -1 itself is negative. So two negatives make it positive. 0.5 minus 1 is negative. 0.5 itself is positive. One negative makes a negative. 2 minus 1 is positive. 2 itself is positive. All positives, so this is positive. So you have increasing, decreasing, increasing. Like I said, we aren't going to worry about a max or a min here at 0, because it's not within the domain. 1, however, is in the domain, so we can have a minimum at 1. But it was important that we included 0 on this sign chart, because it does change at 0 from increasing to decreasing. So there's no max. There's a minimum at x equals 1. We are increasing from -infinity to 0, and then also from 1 to infinity. And we are decreasing from 0 to 1. Any questions on that one? Like I said, if I know I'm kind of going quickly through these, but we are, I guess, 36 minutes in and just on problem 3 right now. So that's why I'm kind of trying to get through it. But if you have questions, please feel free to type them. All right, so now we're looking for inflection points and intervals of concavity. So where is it concave up? Where is it concave down? Right. So your increasing, decreasing, that comes from your first derivative. Your concave up/down, that comes from your second derivative. So these also include the maxes and mins for your first derivative, and this includes inflection points for your second derivative. Inflection points. So we have to take the second derivative here. So we have 3x squared minus 4x. We're not going to do anything with the first derivative. We'll come to the second derivative. 6x minus 4. We'll set it equal to 0. You'll get x is equal to 4 over 6, which, when we simplify, is 2/3. That's the only possible inflection point. We are making a sign chart. I'm going to use 0 and 1. And you're plugging back into 6x minus 4. So plugging in 0, you're going to get a negative. Plugging in 1, 6 minus 4 is positive. And once again, this is the second derivative, so we're not doing like increasing, decreasing. We're not going to do like a down arrow here. Instead, this is concave down, and sad people are concave down. Sad people are down all the time, so it makes a sad face. And then if you are happy, if you are up, concave up, you are a happy face. Because we change inflection at 2/3 and 2/3 is in the domain, it's important that you have both. 2/3 is where inflection or concavity changes, and 2/3 fits within our original domain. We do have an inflection point at 2/3. So I'm going to just write concave up like this. From 2/3 to infinity, we are concave down from negative infinity to 2/3. And we have an inflection point at x equals 2/3. So it's going to be the same process with all of these. We're going to find the first derivative, then we find the second derivative, then we make a sign chart, and then we pull the information off of the sign chart. So we'll start with y prime. We have 4x cubed plus 3x squared minus 6x. Go straight for the second derivative on this one. 12x squared plus 6x minus 6. Setting that equal to 0, we can factor out a 6. We get 2x squared plus x minus 6. Let's see, this one's going to factor into plus 1. It's minus, oh, yeah. I was like, this isn't what I was thinking. Yeah, good call. Minus 1, because you're factoring out that 6. There we go. So this factors into, I think, 2x plus, no, 2x minus 1, x plus 1. Yep. So this factors into 2x minus 1 times x plus 1. You'll get x equal to 1/2 and x equal to negative 1. Choosing test points. Okay. I don't need to plug it into the 6 because 6 is already positive, so we can just worry about these guys here. You only need to worry about plugging into this thing out front in the case where, if you have an x out front, that's when you have to worry about plugging in to this part. But if it's just a constant like we have now, no x, you don't have to worry about plugging into it. So negative 2 times 2 is negative 4, minus 1 is negative. Negative 2 plus 1 is negative. 2 negatives make a positive. 0 minus 1 is negative. 0 plus 1 is positive. So that's going to be negative. 2 minus 1 is positive. 1 plus 1 is positive. 2 positives make a positive. Once again, we are talking concavity, so positive is concave up, negative is concave down, positive is concave up. So we are concave up from negative infinity to negative 1, and from 1/2 to infinity. We are concave down from negative 1 to 1/2. Oh, somebody in the comments said, okay, we got it figured out, yeah. Yeah, it should be, so 2x minus 1 and then x plus 1. And then because we change concavity at both these values, and because they fit within the original domain, we have inflection points at both negative 1 and 1/2. And that's that on that one. All right, one more one of this. So you do have options on how you approach this particular problem. You can do quotient rule here if you want. However, it's a little faster if you recognize this is the same thing as x minus 3 to the negative 1. Makes your world a little bit quicker. Something you might want to note right away, domain-wise, x cannot be equal to 3, right? X equals 3 is not in the domain. So this could still end up, and it probably will end up, being an important value, but it can't be a critical value. So you can't have, it's a possible inflection point if it makes the numerator or denominator 0, but it can only actually be a critical or an inflection point if it's within the original domain of the function. In this case, 3 will not be in the domain of the function, so 3 can't be an inflection point, although you could change concavity there. So taking this first derivative, we'll bring the negative 1 down. So negative x minus 3 to the negative 2. Derivative of the inside is just 1, because the derivative of x minus 3 is 1. So this is just negative x minus 3 to the negative 2. For y double prime, you get negative negative 2 times x minus 3 to the negative 3 times the derivative of the inside is 1. So this is just positive 2 x minus 3 to the negative 3, which would be rewritten as 2 over x minus 3 cubed. Which we can set equal to 0. So like I said, x equals 3 is an important value here. It's an important value. It's a place where we could potentially have concavity change. We have to take it and use it in our sign chart. But we cannot have an inflection point there. So I'm going to kind of make an asymptote line just to remind myself that we cannot have an inflection point at 3. Choosing test points and plugging into our second derivative down here. The numerator is positive. And then negative, if you do 0 minus 3, it's negative 3. Negative 3 cubed is negative. And that comes out to be a negative. Numerator here is positive. 4 minus 3 is positive 1. Positive 1 cubed is positive. So this is positive. We are concave down and then concave up. So we are concave up from 3 to infinity. We are concave down from negative infinity to 3. But once again, even though we change concavity at 3, even though that's happening, because 3 is not in the original domain of the function, we do not have an inflection point. Inflection points graphically look something like this. This like ends up being an inflection point. Or you could have it like that. That's an inflection point. But if you have a graph and there's an asymptote there, like if you had something like this, you can't have an inflection point on an asymptote because an inflection point is talking about the shape of the graph. It's talking about making this type of shape. But you're not actually making that type of shape here. Even though this would go from concave up to concave down, it wouldn't make this shape. So that's why this wouldn't be an inflection point. So there is no inflection points. So with number 4, we're going to find intervals of increase and decrease, x-coordinates of any local maxes or mins, and concavity and inflection points. So basically we're doing everything for this problem. So the first part is going to be the increasing, decreasing, max, min part. And that's going to come from the first derivative. So the first derivative here will be 3x squared minus 12x. Setting that equal to 0, we can factor out a 3x. We have x minus 4 equal to 0. 3x set equal to 0 will give you x equal to 0. X minus 4 equal to 0 give you 4. There's not going to be any domain issues here because we have a polynomial to begin with. So 3 times -1 is negative. -1 minus 4 is negative. 2 negatives make a positive. 3 times 1 is positive. 1 minus 4 is negative. Positive and a negative make a negative. 3 times 5 is positive. 5 minus 4 is positive. 2 positives make a positive. Because this is the first derivative we're talking about, this is the increasing, decreasing. So increasing, decreasing, increasing. So we have a maximum here and a minimum here. So we are increasing from -infinity to 0, and then again from 4 to infinity. We are decreasing from 0 to 4. We have a local max at x equals 0 and a local min at x equals 4. So that is the first part, looking for local maxes, local mins, and then increasing, decreasing. The next part is the concavity part. So we're looking for concavity and inflection points, and that's going to come from our second derivative. So I'm going to start with the unfactored form. All right, so you end up factoring on this step here, but you want to go back to its unfactored form to take that second derivative because it's way easier to take that derivative nearly all of the time. So taking that derivative, I get 6x minus 12 equal to 0. Factoring out a 6, x minus 2 equal to 0. We get 2. We don't have to worry about this 6 out front because he's positive, so he won't change the sign of anything. 0 minus 2 is negative, so it's just negative. And 3 minus 2 is positive. This is concavity, so sad people, negative people are concave down, happy people are concave up. We are concave up from 2 to infinity. We are concave down from -infinity to 2. And then because 2, we change concavity at 2, and 2 is in the original domain, we have an inflection point at x equals 2. And that is the second part of our answer. All right. Dang it, that fly. Driving me nuts. For number 5, we're going to actually start graphing these things. And before we can graph something, we really need to have like all the information. So we're going to find all the stuff. Now, with this function here, the x-intercepts for this function aren't very nice. So I just went ahead and found them for you. I just told you what the x-intercepts were. So in terms of x-intercepts, you have 2 of them given, -0.94, 0, and 0.65, 0. These ones are your x-intercepts. For your y-intercept, that's where you let x equal 0. So y is equal to 0 to the 4th plus 8 times 0 cubed plus 18 times 0 squared minus 10. It's just equal to -10. So your y-intercept is at 0, -10. So you have your x-intercept and your y-intercept. With equations of any asymptotes, this is a polynomial, and polynomials don't have asymptotes. Then we're looking for increase, decrease, and concavity. Right, so our first part was getting the x and y intercepts and any asymptotes. The next part is the increase, decrease, relative max, relative min. For these ones, you want the coordinate points, the maxes and mins, which means you're going to take any x values you get and you're going to plug them back into the original function. So here we're going for that first derivative, g prime of x equals 4x cubed plus 24x squared plus 36x. Set that equal to 0. I can factor out a 4x here, and I get x squared plus 6x plus 9 equal to 0. And this will factor into x plus 3 times x plus 3, which is just x plus 3 squared. So you have negative 3, positive, oh, not negative 3, positive 3. Hold on here. You get x equals 0 and x equals negative 3. I'm so used to difference of squares. So you have negative 3 and 0 that you're plotting here. Choosing test points and then plugging into here. Keep in mind that this guy right here, because he's squared, this guy's always going to end up being positive. You can just write it in. The only thing that matters is the 4x part because this part is positive. And the 4x part really just relies on the number you're choosing. 4 times negative 4 is a negative. So negative. Negative 1 times 4 is negative. 1 times 4 is positive. So we have negative, negative, positive. So we have decreasing, decreasing, increasing. Now, because there's no breaks in here, there's no asymptotes or anything. If you have decreasing on 2 consecutive intervals, you're not actually stopping decreasing. You're not going to write your answer as 2 separate intervals as long as there's not an asymptote there. If you have an asymptote at negative 3, then you would have to break it up into 2 intervals. But if there's no asymptote, it would be more correct to write this as 1 interval because they are decreasing on the entire thing. You're increasing on on 0 to infinity, and then you are decreasing from negative infinity all the way up to 0. Right, this gets combined into 1 interval because you don't actually, the graph doesn't break up here. Negative 3 is in the domain and it's decreasing that entire time. So this is like decreasing, decreasing. Here's where we have a min. There's no local max, but you do have a local min at x equals 0. And if you plug 0 into this function like we already did for the y-intercept, you get negative 10. So this is at the point 0, negative 10. For the next part, we're looking at concavity and inflection points. Once again, for this, it's better to go back to your unfactored original derivative than to try to use this one, just because this becomes a little messier. So back to our unfactored derivative. Taking that derivative, we have 12x squared plus 48x plus 36 equal to 0. You can factor a 12 out. So x squared plus 4x plus 3 equal to 0. This factors into x plus 3 times x plus 1 equal to 0. X equal to negative 3. X equal to negative 1. Grabbing some test points. Negative 4 plus 3 is negative. Negative 4 plus 1 is negative. Two negatives make a positive. Negative 2 plus 3 is positive. Negative 2 plus 1 is negative. One negative makes a negative. 0 plus 3 is positive. 0 plus 1 is positive. Two positives make a positive. And we are talking about concavity because this is the second derivative. So we have concave up, concave down, concave up. So we have concave up from negative infinity to negative 3, and then from negative 1 to infinity. We are concave down from negative 3 to negative 1. And then both of these points are within the original domain, and we change concavity at both of them. So it goes concave up, then concave down. So we change at negative 3, at negative 1, concave down, concave up. So it changes at negative 1. So there are inflection points at x equals negative 3 and at negative 1. Those need to be plugged back into the original equation. So with this guy, if you plug in negative 3 to this equation, I'm just going to tell you that it comes out to be 17. And if you plug negative 1 in, it comes out to be positive 1. So when you're going to draw this graph, because that is the next part here, is sketching the graph, you want to kind of consolidate your information. And there's a few ways, like I like to summarize it for sure, but it also can help to separate the points from the intervals. So for the points, we know that we have x-intercepts at negative 0.94, 0, and 0.65, 0. We have a y-intercept at 0, negative 10. And then for the maximum, or there's no maximum, for the minimum, we have the point 0, negative 10. And then the other points we have are these two down here, which are inflection points. So at negative 3, 17, and negative 1, positive 1. So those are the points that we have to plot. For the intervals, we are increasing from 0 to infinity. We are decreasing, and I'm just rewriting this essentially, from negative infinity to 0. We are concave up from negative infinity to negative 3. And from negative 1 to infinity. We are concave down from negative 3 to negative 1. And now that is all of our information we need to draw our graph. So in terms of the points, if we look at the points, we know that the x values range from, because we can look at the x values of all of these points, now that the points are separated from the intervals, we can look at those x values. So we have two that are kind of close to 1, we have 1 at negative 3, 1 at negative 1. So we know we can kind of get away with making our x values kind of small. So we can kind of spread this out a little bit. So we have negative 1, negative 2, negative 3, negative 4. 1, 2, 3. So plotting these points, negative 0.94, that's really close to negative 1. Negative 0.65, that's a little after 1/2. 0, negative 10. So if we look at the x values that we need to plot, we need to, or not x values, y values. With the y values, we need to include negative 10 and positive 17. And honestly, I'm just going to kind of be lazy with this and put 17 here and put negative 10 here. I'm just going to be lazy and not draw the lines in between. So 0, -10 is right here. We have that point twice. -3, 17. It's like around here. And then -1, 1. So it's like in here somewhere. Cool. Now I'm going to do my little chart that I do at the bottom here. I'm going to take each of the places where my intervals split up and I'm going to make my chart with those locations. So I have -3, -1, and 0. -3, -1, 0. I'm going to make myself some really light lines just to help me kind of draw my graph. So I know that something changes at those points. Those aren't asymptotes. They're just the lightest of light lines to let me know that something happens there when I'm drawing it. All right, so increasing from 0 to infinity. So I know I'm increasing here. Decreasing from -infinity to 0. So I'm decreasing, decreasing, decreasing. We're concave up from -infinity to -3. And then we are concave up from -1 to infinity. We are concave down from -3 to -1. Then I'm choosing the shape. Based on this information, I can choose what the shape is going to be. Remember, there's 4 possible shapes. Essentially, you have concave up decreasing, concave up increasing, concave down increasing, concave down decreasing. I told you before to separate in your head. You kind of take each of these shapes and you kind of cut them down the middle. And that'll show you the different versions. So here we have the decreasing side. This is the decreasing side. This is the increasing side. This is the increasing side. So looking at this picture, decreasing concave up, that's going to be this side of it. So it's going to make this shape here. Decreasing concave down is going to make this shape. Decreasing concave up is going to make this shape. And increasing concave up will make this shape. So all I have to do now is hit all these points and use this information. So in this area, my graph is going to look like this. So I know it's going to be like something like that. Then I know that it changed. And first of all, I know a -3 is an inflection point. So I know it's going to make that change there. And I'm going to make this shape in this region. In this region, I am making that shape. In this next region, I'm making this shape. You don't want it to really make sharp corners there. I'm just doing the best I can. Clearly my graph isn't going to look perfect because I didn't have it on a grid. We just do our best. And then for the remainder of this area, it makes this shape. And you can kind of see how that should go. Just something like this. And that is the graph. If we go on to 5B, this one's going to take a little bit of work. So I'm actually going to write the intercepts and asymptote part down here because this one has a few asymptotes to worry about and intercepts. When you're looking at a rational function, the x-intercept is going to be when the numerator equals 0, because it's when y equals 0, which is essentially going to end up being the denominator being 0 isn't going to give you, and you can't have an intercept where the denominator equals 0. You would only have an intercept if the numerator equaled 0, because that's the only way you could equal 0 is if the numerator equals 0. So you have negative 3x squared equal to 0, which just gives you x equal to 0. So that's going to be the point 0, 0. And I'm going to start collecting that information over here. For the y-intercept, this is where you plug in x equals 0. So y is equal to negative 3 times 0 squared over 0 squared minus 4. That's 0 over negative 4, which is just 0. That makes sense. I've said this before. If you have the x-intercept 0, 0, it's also your y-intercept. So this is really like x/y intercept because it's both of them. For your asymptotes, you have a vertical asymptote when the denominator equals 0. So in our case, x squared minus 4 is the denominator. So this will be x plus 2, x minus 2 equal to 0. You get x equal to negative 2 and x equal to positive 2. So you have vertical asymptotes at both of those, at x equals negative 2 and x equals 2. So maybe right above here, I'm going to give room for asymptotes. So vertical asymptote at x equals negative 2 and x equals positive 2. For your horizontal asymptotes, this one is where you take the limit as x goes to positive and negative infinity. So we have the limit as x approaches infinity of the original equation, which is negative 3x squared over x squared minus 4. With rational functions and limits, when you're going to infinity, you can just take the highest power. So limit as x goes to infinity of negative 3x squared over x squared. Those x squareds are going to cancel, and you're going to get negative 3. So that means there is a horizontal asymptote at y equals negative 3. Horizontal asymptotes are always of the form y equals. Now, if you do the asymptote in the other direction, it's going to end up the same. Some cases it doesn't, but in most cases it will. Because if you take this asymptote, it's going to come down to the same math, right? You're going to do the same math, and at the very end, that math didn't matter. You're not plugging infinity or negative infinity in because all the x's cancel in the end. So we have a horizontal asymptote at y equals negative 3. The next part is for increasing, decreasing, and then maxes and mins. And our original function is right here, just so you know, you have it for quick reference. It's on screen, it's right here. maybe I'll rewrite it. What was the name of the function p of x? This is going to be a situation where we need to use quotient rule. So we have that f is equal to negative 3x squared. Maybe I'll write this differently. F is equal to negative 3x squared. So f prime is equal to negative 6x. G is equal to x squared minus 4. So g prime is equal to 2x. Taking this derivative, f prime g, so we have negative 6x times x squared minus 4 minus g prime f, so minus 2x times negative 3x squared. All over g squared, so that's x squared minus 4 quantity squared. Simplifying this, we have negative 6x cubed plus 24x plus 6x cubed all over x squared minus 4 squared. Those 6x cubes are going to cancel, and you get 24x over x squared minus 4 squared. Now, I know I can factor this, but I also know that the zeros that come out of this are going to be 2 and negative 2. So I'm not even going to bother factoring it, because when I go to take my second derivative, I'm going to want it in this form anyway. So what I'm going to do is simply just write x equals negative 2, positive 2, because I know that's what it's going to come down to, and x equals 0. So we have negative 2, 0, 2. Choosing our test points, x equals negative 3, x equals negative 1, x equals 1, x equals 3. This denominator is squared, so it's always going to be positive. So I know because this thing is squared, it's always positive. I can just write it in right away. So I'm just looking at the numerator, and the numerator is just taking our x value and multiplying by 24. So as long as your x value is negative, the numerator is negative. If your x value is positive, your numerator is positive. So this will be negative, negative, positive, positive. So we have negative, negative, positive. That's a plus right there. Positive. So decreasing, decreasing, increasing, increasing. And something I do that I didn't do here, I like oftentimes to keep note of the fact that we have these vertical asymptotes at negative 2 and 2. So most of the time when I'm doing this, I don't want to, see. Most of the time when I'm doing this, I'll like draw asymptotes in to remind myself that I have asymptotes there. So you can't have any maxes or mins there, and you also can't include those values when you do your intervals. So we are increasing from 0 to 2, and you do have to break up at 2 because 2 is not in the domain of the original function. The original function had x squared minus 4, so you can't include 2. So then you would split up at 2 and go to infinity. We are decreasing from negative infinity to negative 2, and then again from negative 2 to 0. We only have one area we need to worry about. We have a minimum, so there's no max. And there's a min at x equals 0. And we already know that that point, x equals 0, if you plug 0 into this function, you get 0. So we already found that point. That was the point 0, 0. So I'm going to copy that information right up here with my summary of information. So this point 0, 0, where's my draw button? There we go. This is also our minimum. So I'm not going to relabel it. It's the x-intercept, it's the y-intercept, it's also the minimum. I'm going to leave a spot for inflection points in case we have any inflection points. And then I'm going to write the intervals down. So we have these guys right here. Just to kind of keep my information as organized as possible. For our concavity and our inflection points, I am coming back to this. This is the most simplified version of my derivative, so I'm going to come back to this one. You want it simplified, but not overly factored. This one, I mean, the denominator is quote unquote factored, sort of, but this is really as easy as it's going to get for us. So we're going to use this version when taking the second derivative. So p prime of x is equal to 24x over x squared minus 4 squared. Doing quotient rule again, so we have our f and our g. F is equal to 24x, so f prime is equal to 24. G is equal to x squared minus 4 quantity squared. Chain rule here. Bring the 2 down, reduce the exponent by 1, and then the derivative of the inside is 2x. So that comes out to be 4x times x squared minus 4. So p double prime, that'll be f prime g, so 24 x squared minus 4 squared minus g prime f, so 4x x squared minus 4 times f is 24x, all over g squared. So x squared minus 4 squared squared. Now, because these guys have an x squared minus 4 in common, I'm not going to FOIL this out. I'm not going to distribute here. I am going to combine together these guys. So I'm going to combine these together. 4 times 24 is going to give us 96. So I have 24 x squared minus 4 squared minus 96 x squared times x squared minus 4. On the bottom, we have x squared minus 4 raised to the 4th power. So from here, what we can factor out, each of these have an x squared minus 4 in common, and they also have a factor of 24 in common. So I can factor out a 24 x squared minus 4. When I do that, all that's left here, if I factor out if I take his 24 away, that's gone. And if I take one of his x squared minus 4s away, I have an x squared minus 4 left, minus 96 divided by 24 will give you 4. So he'll have a 4. He'll still have the x squared. He'll have this x squared. But you took away his x squared minus 4, so he won't have that anymore. All over x squared minus 4 raised to the 4th. From here, you can cancel one of these x squared minus 4s. So this would become a 3. So there's 1 on top, there's 4 on the bottom. Cancel one of them, you'll be left with 3 on the bottom. So I have 24. Here, so x squared minus 4x squared, that's negative 3x squared minus 4 over x squared minus 4 to the 3rd. The only thing additionally you may want to do here, Because these are both negative, you could factor that negative out. So you'd have negative 24, and this would be 3x squared plus 4 over x squared minus 4 quantity cubed. Whew. So the derivative is the hard part there. From here, the negative 20, there's no x in front of here, so we don't have to worry about x equals 0. 3x squared plus 4 is a sum of squares, and sum of squares will never equal 0. Down on the bottom, we know we get x equals negative 2 and positive 2, and that there's asymptotes at both of those. So here's a few things going on here. There's always a negative 24 in front. I'm going to write this in. Before I even choose test points, I can do this. I know there's always a negative 24 in front. And additionally, 3x squared plus 4, it will always be positive. A sum of squares is always positive. So I know that there's going to be a positive in the numerator. The only thing I really have to plug into is this bottom part down here. So when I choose my test values, negative 3, 0, 3, what I'm doing is I'm plugging them in down here, and basically that's the only thing I have to do because up here is already set in stone. So negative 3 squared is 9. 9 minus 4 is 5. 5 cubed is a positive number. So this will be negative. 0 minus 4 is negative. A negative cubed is a negative. 2 negatives make a positive. 3 squared minus 4 is going to be 5. 5 cubed is positive. This will be negative. So we have concave down, concave up, concave down. So we are concave down from negative infinity to negative 2, and from 2 to infinity. We are concave up from negative 2 to 2. And then even though we change concavity at negative 2 and 2, because these are asymptotes, we do not have inflection points there. There are no inflection points because they are asymptotes. We cannot have an inflection point at an asymptote. So with that in mind, I can put that information over here. Bam. We have none. So we have no inflection points, so we don't need to worry about that. We only have one point to plot, and then the rest is just concavity and then asymptotes. So we know if we have vertical asymptotes at 2 and negative 2. We know that we have a horizontal asymptote at negative 3. We have this point 0, 0 that we can plot. So I've plotted these guys. Now it's time to break up the rest of my chart down here. I already broke it up at negative 2 and 2. We just have to look for if there's any additional numbers. I don't think that's supposed to say 0, is that? Is it increasing, decreasing? Oh. Yeah, it is. Okay, just kidding. We're good. So we need to put 0 on there, and that's the only other place we have to worry about. So the places where stuff changed, because in this case, they're already kind of like there's already kind of markers at the places where they change. You don't really need to really add that note for yourself. But if you want to add that note for yourself about where they change, you could totally do that because you know something has to happen here, and happen here. So for increasing, we are increasing from 0 to 2, and then from 2 to infinity. We are decreasing from negative infinity to negative 2 and negative 2 to 0. We are concave down from negative infinity to negative 2, and then from 2 to infinity. And we are concave up from negative 2 to 2. So drawing those shapes in down here, decreasing concave down, that's going to make this shape. Decreasing concave up will make this shape. Increasing concave up will make this shape. And increasing concave down will make this shape. So the rest of this is just filling things in. We know that this point right here is a minimum, and based on the way that this graph looks here, we know we want to turn around here because the graph has no other x-intercepts. So we can't like go and then go down here. We can't do something like this. We want the minimum to be here. So just keeping in mind in this middle section that this has to be a minimum. Here, you know there's no more x-intercepts, and it doesn't make sense to have the function doing something like this because there's a horizontal asymptote we have to take care of. So the only really choice is like you're choosing between these two shapes here. And because there's no other x-intercept and because the top shape doesn't make any sense, it has to be this one. For the middle section, we're making this shape, hugging those asymptotes. We're not passing them, we're hugging them. And then once again, your choices, you're really choosing from these two shapes. And the only ones that match are going to be these guys. And so that is the final look of your graph. And that is that on that problem. A lot of lead up to that. But there we go. So going to this next problem here, I want to see if I have a graph on here that I can use. That one will work. So for number 6, you are sketching a graph that has some conditions. And you kind of want to just go through these and plot them. So first of all, continuous everywhere except for negative 2 and 3. Typically that means there's asymptotes there. And if you go down to the next statement, there are asymptotes at negative 2 and 3. So I'm going to come on here and I am going to draw in my asymptotes. And I know that my graph is going to have to break up there, so I can start drawing my graph, my chart right below here. In terms of points, we've been given 3 points to plot. So we have the point 0, 0, we have the point 2, 2, and we have the point 4, 0. We want to plot those points. So we have 0, 0, we have 2, 2, and we have over 4, 0. Something to keep in mind here is we might not have been given all the intercepts. There might be additional intercepts that we were not given. All we know is that these points are for sure on the graph. This next line, where it says the limit as x goes to infinity is negative 2 and negative infinity is negative 2, that means there's a horizontal asymptote at y equals negative 2. So we need to draw in that horizontal asymptote. For the graph, the chart down here, we're looking at these intervals and where they split up. So they split up at -2, we got that one, 0, +2, got, no, we don't have +2, so 2, we have 3, 0, -2, we have 1. Oh my goodness, 1. And yeah, that's what we have. So I'm almost wondering if I should just hand draw this so I can make my graph a little bit less cramped, because it's going to get really cramped in there. It's going to get really cramped in there. I think that's what I'm going to do. I'm just going to hand draw it so that it's not super cramped, because it's going to be really cramped otherwise. And it doesn't take a long time to redraw. So we have -2, 3. Oh, I put the asymptote in the wrong spot. Hold on. The asymptote was at 3. We split up at 0, 1, and 2. Oh, hold on, mute myself. I think they're good. Okay. Sorry about that. So then plotting some points here. Oops, got the wrong thing there. Well, I was going to draw my guiding lines. That's what I was going to do before my dogs rudely interrupted me. So just making these lines just so I have an idea of where my graph will change shape. And my points, we have 0, 0, we have 2, 2, and we have 4, 0. We are increasing, so f prime greater than 0 means increasing. Your first derivative is positive, so increasing. So -∞ to -2. And then from 0 to 2, we are decreasing. So f prime is negative, means decreasing from -2 to 0, and from 2 to 3, and then from 3 to infinity. F double prime positive means you're concave up. So you're concave up from -∞ to -2, from -2 to 1, and then from 3 to infinity. And then you're concave down from 1 to 3. Choosing the shapes. Increasing concave up is going to make this shape here. Decreasing concave up will make this shape. Increasing concave up will make this shape. Increasing concave down will make this shape. Decreasing concave down makes this shape. And decreasing concave up makes this shape. So going in to draw this here, what we know with asymptotes is that if with the horizontal and vertical, you're really choosing between these two shapes in this area. The only one that matches would be this guy. So you know it has to hug the asymptote. So as your graph leaves the page, you hug the horizontal. It's okay to cross a horizontal in the meantime, but you can't, as your graph is leaving the page, you have to be hugging it. So we're hugging it here and we're hugging the vertical. And then in this region here, we are making this shape. There are no particular points we have to cross until here. So we know we have to cross here, and we know it needs to make this shape because it needs to hug the asymptote. In this area here, we're making this shape. And then in this area here, we're making this shape. So we know we kind of have to, at some point, kind of change. So we're making this upward cup shape. Then we're changing to this downward cup shape because there's an inflection point there. And then in the next area, we are making this shape, and it has to hug the asymptote. So if it's making that shape, it goes all the way down. And then finally, for the last one, again, you're choosing between these two shapes. Obviously, only one of those matches the shape that we're supposed to make. So we want to hug the asymptote. We want to cross where they told us we had to cross. And we want to hug the vertical asymptote going outward. And that is the glorious graph of this problem. I guess now is a good time to ask, like, are there any questions up to this point? Up to this point, are there any questions? Because we're about halfway done, and it's been 2 hours, and I think the rest of it will go a little bit quicker. I'm hopeful. Okay. All right. So let's talk about this number 7. This one, you're matching the original graphs, like you could think of these guys as your f. You're matching it to its derivative, f prime. So here's the thing you're kind of thinking about. If your graph is increasing, if f is increasing, that means f prime is positive. And being positive means you're above the x-axis. That's what being positive means. You're above the x-axis. So if f is increasing, f prime has to be positive. If f is constant, so it's just making like a flat line, that means f prime is equal to 0. That's on the x-axis. And if f is decreasing, that means f prime is negative, which is being below the x-axis. Hold on just a second. Toad, stop that. My dog has a cone on. I think I've talked about him having a cone on at this point a lot, but he has a cone on, and he likes to lick the cone. And the sound of him licking the cone just drives me nuts. He also likes to sit right next to me while I'm doing anything. So he's sitting right here looking at the cone, making me crazy. All right. So now we're just matching all these graphs. We're matching A, B, C, and D. And there's extra graphs in here. So they're not, obviously there's going to be 2 extra F primes in there. So if we're looking at this, we are increasing on this area here. We are increasing. That means that f prime, when we go to the derivatives graph down here, should be above the x-axis up until 2. So it can't be this one. It can't be this one because those ones are on the x-axis. This one is possible, right? Because we have that above the x-axis. This one's possible. We'll talk about that in a moment. This one's possible, but this one's not. Now, with all of these, you have a constant section, which I said that means that it would be on the x-axis in the derivative, And with all of these, you have that going on. So we have to choose between these what's going on. Now, this right here is the shape of a line, right? This is a line shape right here. This is like a y, oops. This is like a y equals mx plus b situation. And if you take the derivative of a line, you just get a solid constant number. And the way that you draw just a number, if you have y equals a number, that's a line. That's a horizontal line. So it can't be these guys here because these ones are actual mx plus b lines themselves. The only possibility here is that you are a solid line here. And it would make sense also because the derivative here, up 1 over 1, the derivative is 1, right? That's the slope of this line. The slope of that line is 1. So it makes sense that you're at 1 right here. So number 3 has to be our option there. And I can erase all that. And then I can cross 3 off the board because we've already decided that 3 is gone. For part B, you start off constant, right? You start off constant, which means that you should be on the x-axis. So from 0 to 2, you should be on the x-axis. That's this one, and this one. So we can cross out these guys because you're not on the x-axis in those parts. The next part is decreasing. This part right here is decreasing. And that means it should be below the x-axis. So this one's below the x-axis, this one's below the x-axis. Number 6 is not, so we'll toss that one. We can't do that one. So now we're just choosing between 1 and 2 at this point. And here's the thing, this is not a solid line here. This actually looks like it's kind of like a parabola type shape. Right? It looks like it's a parabola type shape. You'll notice that it has a really steep slope at first, but then it gets more shallow. A steeper slope would be a more negative slope, whereas a shallow slope, like it looks like it almost has a slope of 0 at the end, right? Because it's going to like kind of stop there. And you notice that this one goes to 0. So it's like really steep to really shallow. It has to be that here. Another reasoning for that is that this part looks like it's like a parabola. Like I said, it looks like a parabola, which would have that equation. And the derivative here would be 2ax plus b, which is, this is just an mx plus b. That's just a line. So the derivative of a parabola is a line, and it would align with slope, not equal to 0, with an actual slope. So it can't be this one. It can't be 1. It has to be 2 here. If you have this parabola type shape, the derivative is going to be a line. So b has to be 2. And we can cross out 2 so that we don't need to look at it. Looking at part C, we do have an increasing portion up until 2. And again, it's a parabola. So if it's a parabola type shape, this is not a line, this is a parabola type shape. We know it's going to be a line in the derivative. If it's a parabola here, it's a line in the derivative. And we know it's increasing. You know, it's increasing. So if it's increasing, it needs to be above the x-axis. So if I look from 0 to 2, it should be above the x-axis. Can't be this one. Right? There's this option here. There's this option here. And we can't use this one because it's not above the x-axis. Notice that it's more steep and then it flattens out to the point where the derivative is almost 0. So it flattens out to the point where the derivative is almost 0. The derivative would be 0 right down here. Right? It doesn't get more steep as we get up here. It gets less steep. So it's like more steep, then less steep, and it gets to 0. So number 5, there's only 2 we're choosing from at this point. Number 5 makes the most sense. Now, it also makes sense because if you look at this next part, it's constant, so it should be on the x-axis. Both of them fit that, but both of them fit that, but this one right here makes the most sense purely because of the parabola shape here and that it flattens out and goes to slope of 0. So it's also differentiable the entire way. And notice that this thing has no holes in it because it's differentiable the entire way. The rest of them will have holes in them because they're not differentiable at these cusps or corners. So part C is going to be 5. Oops. 5. Choosing for part D, if you go for the quote-unquote easy part first, we know that it is flat from 2 to 4, so it's going to be on the x-axis for the derivative from 2 to 4, so it can't be this one. This one works, and then it can't be this one because from 2 to 4, it's down here. So the only one that works, we don't even have to look at the rest of it, the only one that works is going to be number 4. And that is that for that. Fun problem. The rest of these problems are going to be pretty conceptual except for the optimization ones. So there's going to be a few graph ones. So there's 8, 9, and 10 are graph ones, and then 11, 12, 13, 14 are optimization. So these ones are just kind of conceptual and we have to think about them. So here's the information you're given. This right here is the graph of f prime. All right. All we know is the graph of f prime. We do not know the graph of f in this particular scenario. This is actually taken from like an AP test, like an old AP test. So this is like an AP test problem. So it says, for -5 to 5, find all values of x at which f, the graph, not the graph we have, but the graph, this is its derivative, the graph we don't see, has a relative minimum. Has a relative minimum. Okay, well, we can think about the things that we know, right? We know that if f has a minimum, right? So it's a minimum right here. We know that f prime is going to be 0 at that point. And we also know that it goes from decreasing to increasing. So you go from f goes from decreasing to increasing. If you're going from decreasing to increasing, that means that f prime goes from negative to positive. Negative meaning below the x-axis, and positive meaning above the x-axis. Right, so this is just, you have to just write down, I do this when I was doing the answer key for these problems, this is literally what I was writing down, right? If f has a minimum, I know that f goes from decreasing to increasing. I know if f is decreasing, f prime is negative. And if f is increasing, f prime is positive. So you're looking for places where you hit the x-axis, because this right here, f prime being 0, that means the graph of f prime has an x-intercept, because equaling 0 means you're hitting the x-axis. So the possible points you're looking at are these points here. Now you want a point where it goes from negative, so you want it below the x-axis, to above the x-axis. So the below parts, right, this is a below part, this is a below part. The above parts, this is an above part, this is an above part. So if you're going, here it's going from positive, so it's positive to negative, so that's not going to work. But right here, you go from being below to being above. Okay. So you only in one place does this happen. Here it goes from above to below. So only in one place does this happen, and it happens at 1. It happens at x equals 1. It has a relative min. Moving on to part 2. Part 2 is asking for, once again, same graph. We have the graph of f prime, and we want all values of x at which f has a point of inflection. Okay. F has inflection point means we have to just write this down, right? If it has an inflection point, we know that f double prime is going to be 0. We know that f double prime has to change from positive to negative or negative to positive, right? Because it means that f changes concavity there. So f prime has to either, you have option 1, go positive to negative, or 2, go negative to positive, because that would be changing concavity. But we don't have the graph of f double prime. We have the graph of f prime. That's when you have to think backwards a little bit. F double prime is the derivative of f prime. So if f prime is increasing, that means f double prime is positive. If f prime is decreasing, that means f double prime is negative. So we're looking for places where f prime, the graph we have, where f prime changes from increasing to decreasing or decreasing to increasing. We're looking for the places where it changes, increasing, decreasing, decreasing, increasing. Those are the places. Also, this f double prime dne is also a possibility here. I should write that down. So we're looking for those places where it changes, increasing, decreasing. That's what we're looking for on this graph of f prime. So if we look, we are increasing, increasing, decreasing, decreasing. So the places where we change right here, we change right here, and we change right here. So those are our inflection points. We have inflection points at -4, -1, and 2. Those are the inflection points. For the third part, we're looking for the intervals on which f is concave up. F is concave up if f double prime is positive. Once again, f double prime is the derivative of f prime. So it talks about the slope of the tangent line of f prime. So if f double prime is positive, that would have to mean that f prime is increasing. So really what this is asking for, since this is the graph of f prime, we're looking, oh, hold on just one second. Sorry about that. So really we're looking for the places on this graph that we are increasing. Just on this graph, because this is the graph of f prime, where are we increasing? We're increasing here, we're increasing here. So we are increasing from -5 to -4, and from -1 to 2. Sorry, let me record again. For the final part of this problem, we're looking for find all intervals on which the tangent lines to f have a positive slope, right? The tangent lines to f have a positive slope. When we're saying this, this kind of means two things for us. It means that f is increasing, or you could say that it means that f prime is positive. Because if f's tangent lines have positive slope, that means that the derivative is positive there. And being positive, because f prime is the graph we're looking at, means above the x-axis. So where are we above the x-axis? So all we have to look for is the places where we are above the x-axis. So those intervals are -5 to -3 and 1 to 4. So with these problems, it's just really important that you write down what you know. I can't say that enough about these problems. Writing down what you know is everything. You have to write down everything here. And then just extrapolate from there. So going into number 9, it's again graph problem, and you have to look at what you have. So this is the graph of f prime. Once again, the graph of f prime. We don't know what f looks like, we just know what f prime looks like. Identify the critical points of f. So those critical points of f are going to be the places where f prime is equal to 0 or f prime does not exist. Because this is the graph of f prime equals 0 just means that it touches the x-axis. Touches the x-axis. So it's like an x-intercept. So there's going to be 3 of them, 3 critical points of f. These are not critical points necessarily of f prime, right? This one is, but these guys aren't critical points of f prime. They're critical points of f, the graph we cannot see. So we have -3, 2, and 5. Those are the critical points of f. Once again, same graph, part B on this one. Identify intervals of increasing/decreasing, intervals of increase/decrease is what that should say, on f. This again is f prime. So if f is increasing, f prime is positive, which means it's above the x-axis. If f is decreasing, that means f prime is negative, which is below the x-axis. So for increasing, we have to be above the x-axis. So this is above, and this is above. So we are increasing from -∞ to -3, and from 5 to infinity. And then we are decreasing wherever we are below. And we'll just say. Now, technically, you could say that it hits 0 here, so it's not below, but I'm not gonna get into those details here. I'm just gonna say it's below the entire time, so it is decreasing that entire time from -3 to 5. For part C, once again, same problem. This is the graph of f prime. Identifying where f has local maxes or mins. So if f has a minimum, right, it would look something like this. It would go from decreasing to increasing. If f is decreasing, this means f prime negative. That should be a prime. If f is increasing, that means f prime is positive. Because this is the graph of f prime, being negative is going to mean below the x-axis, and f prime being positive means above x-axis. So it's going to have a minimum where it goes from being below to being above. Now, it only has one point where it does that, right? Right here, it goes from below to being above. So there's a minimum. F has a minimum at 5. If f has a maximum, it's just the opposite of that. It means we go from increasing to decreasing. So it means we go from f prime being positive to f prime being negative. So it goes from being above the x-axis to below the x-axis. So from being above, right here, to below, we only happen at one point here, it's at -3. For part 9D. 9D. Once again, same graph. This is f prime. Identify intervals on which f is concave up or concave down. So f is concave up if f double prime is positive. And if f double prime is positive, that means that f prime is increasing. This is kind of that same concept we talked about before. So we're looking for places on the graph where f prime is increasing. We are increasing here, and we are increasing here. So we are concave up from -1 to 2, and from 4 to infinity. This is what f is concave up. F prime itself is not concave up on those intervals. It is f that is concave up. If f is concave down, that means f double prime is negative. If f double prime is negative, it means f prime is decreasing. So we are decreasing on these intervals. Oops. So we are concave down from -infinity to -3, or not -3, -2. Or is that -1? Let's call it -1. Or I guess in the answer key, I call it -2. I don't know. It's somewhere between -1 and -2. It's hard to tell down here where exactly that is. Maybe -1.5. It doesn't matter though. Close enough. And 2 to 4. And that's the answer for this guy. So the last part of this problem is identifying the inflection points of f. This is where f changes concavity. F changes concavity if you have f double prime going from positive to negative, or if f double prime goes from negative to positive. Right, that would be changing concavity. Now you could use the intervals you had in the last one to figure this out, but we'll just do it from scratch here. Because we're looking at the graph of f prime, f double prime positive means f prime increasing to f prime decreasing. There's a location where we go from increasing to decreasing. So here we go from increasing to decreasing. Right? So that's an inflection point there. We don't have any other places where we go from increasing to decreasing. F double prime is negative means f prime is decreasing. F double prime positive means F prime is increasing. So places where we go from decreasing to increasing, decreasing, increasing. Here at, I'm going to call it -1. I think I called it -2 in my answer key, but it doesn't matter. Somewhere between -2 and -1. And then another place right here, we go from decreasing to increasing at 4. So in total, we have -1, 2, and 4. That is the last part of 9. And we'll move on to 10, which is the last graph. All right. This is actually the same graph, but it is now the graph of F double prime. So now it's not the graph of F prime anymore. We're changing gears, and this is the graph of F double prime. So inflection points of F, we can kind of go back to previous problems here. Inflection points of F, I have to do select. All right. An inflection point of F is going to be where F changes concavity. So it's places where F double prime goes from positive to negative or negative to positive. We don't need this information about F prime anymore. We're actually looking at the graph of F double prime. So F double prime positive means F double prime above x-axis. Since this is the graph of F double prime, right, above x-axis to below the x-axis. Which is all of this in here. So it's places where it goes from being above to below, or going from below to above. So there are 2 places where we go from above to below, or below to above. So this would be at x equals -3 and x equals 5. Part B of this problem asks where F is concave up or down. If F is concave up, that means F double prime is positive, which means it's above the x-axis. So F is concave up from -infinity to -3 and from 5 to infinity. F is concave down if F double prime is negative, which would be being below the x-axis. Once again, this is the graph of F double prime up here. So F is concave down. If you're below, you are in this region here, from -3 to 5. And that is that on this problem and all the graphs. So we only have 4 problems left. They are all the optimization problems. I'm hoping it doesn't take me too long to get through those because I am starving at this point. So let's get through it. All right, so for our first optimization problem, we are finding 2 positive numbers such that their product is 192 and the sum of the first plus 3 times the second is a minimum. So the first part is a constraint. We have 2 positive numbers such that their product is 192. So x times y is equal to 192. And then the sum of the first plus 3 times the second is a minimum. Okay. I'm just going to call this function f. The sum of the first, so x is the first, plus 3 times the second is a minimum. So we need to plug in, we need to plug in either x or y in here so that we only have x's or y's. It doesn't matter which one you do here. most of the time I like to have x's, so I'm going to solve for y here. So y is equal to 192 over x, and I'm going to plug that in. X plus 3 times 192 over x. Just double checking, making sure. Yep. So you have x plus, I'm going to write this as 576 and then x to the negative 1. So taking the derivative here, we have 1, and then it's going to be minus 576 x to the negative 2. Setting that equal to 0. This is 1 minus 576 over x squared. Making a common denominator here, multiplying by x squared on both sides. We have x squared minus 576 over x squared equals 0. Now, the original did say that both the numbers are positive. So really, so you're going to get like x squared equals 576. Take the square root, you get x equals plus or minus 24, because that's the square root of 576. But because it said that they had to be positive, the positive is the only option here. Down here, you'll get x equal to 0, but again, they had to be positive, so we can't use 0. So 24 is the only option. We do need to check it. We need to verify that 24 works. I'm going to go back to this guy. I'm going to find f double prime and then see what the concavity is. So f double prime, you're going to have negative 2 times 576 x to the negative 3. So you end up with 1152 over x cubed. If you plug in your 24, so you try f double prime of 24, that's 1152 over 24 cubed. That's going to be a positive number. So f double prime positive means you are concave up, which means you have a minimum, which is what we wanted. It said minimum. So for our answer, we do have x is equal to 24, and then y should be equal to 192 divided by x, which is 24, which gives you 8. So the two numbers are 24 and 8. So you're making sure to double check that it is a minimum. All right, for the next problem, a company determined that its cost function is given by this function right there. If the company can produce at most 8 shipments, find the quantity of shipments that will yield absolute max and minimum, max cost and minimum cost. So again, this is a problem where there's some stuff built in here because they say you can produce at most 8 shipments, and what they're not saying is that the least amount of shipments they can produce is 0. So you are on an interval here. You can produce at minimum 0 and at most 8. So this is a domain restriction we have. This means that we're going to be finding absolute max and min, which means finding critical values and then plugging them back into the original function along with the endpoints. So taking the derivative, you're going to get negative, if you bring the 3 down, they just cancel, negative x squared plus 6x minus 5. Is that equal to 0? Factoring out the negative, negative x squared, negative parenthesis x squared minus 6x plus 5 equal to 0. This would be x minus 5, x minus 1 equal to 0. X equal to 5 and x equal to 1. And we're plugging all of these plus these into the original function, which was c of x. So c of 0, if you plug in 0 up here, you're just going to get 100. C of 1, so negative 1 cubed over 3 plus 3 times 1 squared minus 5 times 1 plus 100. Thank you, Toby. Making a lot of noise. Right. It comes out to 97.67 when you round it. I am using all these numbers, by the way, because they are within the domain. I can use both 5 and 1 because they fit in here. If either of these were outside the domain, I would not be able to use them. So I have negative 5 cubed over 3 plus 3 times 5 squared minus 5 times 5 plus 100. And I believe that comes out to be 108.33. And then finally, the last endpoint, which is 8, negative 8 cubed over 3 plus 3 times 8 squared minus 5 times 8 plus 100 should give approximately 81.33. So if you're talking about minimum and maximum, the smallest number on here is here. It's the min. And the maximum number on here is here. So it asked for both. It asked for the absolute min and max. It asked for the quantity. So the minimum cost is with, let's see, 8 shipments. And the maximum cost is at 5 shipments. And we don't need to do any verifying because the verifying is done right in here. When you're checking those points, when you're doing the absolute ones, you are verifying it just by plugging in. So that is the second optimization problem. My husband is cooking a frozen pizza right now. It smells really good. So we're going to get through these so I can eat some pizza. All right. Number 13, a gardener wants to make a rectangular enclosure using a wall as one side and 120 meters of fencing for the other 3 sides. Find the dimensions of the rectangle that provide the greatest area. So here's kind of what we have going on. This is a wall. And then we want to use the wall to make a fence. So all of these sides right here, there's 3 sides that are made of fence. And we have 120 meters of fencing. So we know that these 2 sides, the opposite sides from one another, have to have the same length because it's a rectangle. And we know that this third side would have a different length, potentially. So the perimeter has to add to 120, right? Like not the full perimeter, but like these 3 sides have to add to 120 because that's how much fencing we have. So we know that 120 has to be equal to x plus y, i.e. 2x plus y. So 2x plus y is equal to 120. That is our constraint. We are optimizing the area. We want the greatest area. We want to maximize area. So the area of this, it's just length times width, x times y. So I'm going to solve for y here. you're going to get y equals 120 minus 2x. And I'm going to plug that in. Hold on just a second. So we have area is equal to x times 120 minus 2x. I'm just going to expand it. 120x minus 2x squared. Take the derivative. So 120 minus 4x, set it equal to 0. You'll get 4x is equal to 120, x is equal to 30. We want to verify that this is actually a max. So I'm taking this guy right here, and I'm going to find a double prime to do the second derivative test. Okay, so a double prime is -4, which is less than 0. So we are concave down, which is a max. So that means x is equal to 30. Y is equal to 120 minus 2 times x, minus 2 times 30, which will give you 60. The question itself was asking for the dimensions of the rectangle, so it's a 30 meter by 60 meter rectangle. And that is that on that problem. This last optimization problem is the one that is the little bit the longer. So with this last optimization problem, we want to construct a box whose base length is 3 times the base width. The material used to build the top and the bottom costs $10 per foot squared per square foot, and the material used to build the sides costs $6 per square foot. If the box must have a volume of 50 feet cubed, determine the dimensions that will maximize or minimize the cost to build the box. So I'm going to draw my box on here. Right? And I'm going to kind of go through all the stuff I know. So there's some information about building materials. So we know the top and bottom are $10 per square foot. And that the rest of the sides, the 4 other sides, are $6 per square foot. And we're trying to minimize the cost of the box. So there are 6 sides total on this box. Right? You have the top and the bottom at 10 square feet, and then there's 2 sets of matching sides. For the 4 other sides, there's really 2 pairs. There's like this side right here, like the purple side, and then there's 2 of those purples. There's one on the other side, and then there's that green side. I'm going to call this guy the length, the width, and the height. What this ends up coming down to when we make the cost function, the cost of this function, we're going to end up having W as a, it doesn't matter. The cost of this is going to be for the top and bottom. So you can find the area of the blue square there, and it's $10. You have 2 sides, and then times the area of the blue, right? Because this is the cost per square foot. You'll have 2 of these blue sides, and then you want the area of that. Plus, the next one is $6. You have 2 purple sides, so you want 2 times the area of the purple. I guess this can go down here. And then the remaining sides are the green sides. Those are $6 per square foot as well. You also have 2 of those. and the area of the green. So now let's go through with, this is what our cost function is going to look like. Let's go through and pick apart what is left. So we want to construct a box whose base length is 3 times the base width. So this length is actually 3W. And maybe actually, give me a moment here. It is 3W, but I think what I'm going to do here is I'm going to talk about this equation in terms of L, W, and H first, and then I'll come back. So the area of this blue square up here, imagine this side right here is W, this side is W, this side is L, this side is L. So the area of the blue is length times width, or width times length. The area of the purple, right, it's a square right here, height times length. And the area of the green is width times height. So I'm going to write this out so then I can make the substitutions in just a moment. But 10 times 2 is 20, so you'll have 20 WL. 6 times 2 is 12 HL plus 12 WH. So we need to make only one variable happen there. So we need to eliminate W's or H's, or W's and H's, or L's and H's, or we need to eliminate 2 of them. There needs to only be one variable. Now I'm going to come back and do my substitutions up here. So this length right here, it says the length is 3 times the base width. So instead of L, I'm going to write this as 3W. And then what else do we have? That's it in terms of the information they've given us. So they've given us W and 3W, but then they also tell us right in here that the box has to have a volume of 50 cubic feet. So the volume has to be 50. But the volume of a box is the length times the width times the height. We've already discussed that the length is 3W, right? That was right here. We have W and then H. So if the volume is 50, it's also equal to 3W squared H. Now it's going to be a tiny bit messy here. Solving for H would be easiest. However, we already know this side in terms of W's, so we really want H to be in terms of W's as well. But you do have an option here. So, oh no, this worked out good. Just kidding. I was thinking of solving for W in my head. Solving for W would make this really messy. But you're solving for H, so it's fine. Just kidding. Ignore that. Divide both sides by 3W squared to get H by itself. Things are going to work out really nice. So you get H is equal to 50 over 3W squared. So here are the substitutions. This right here was length. Length is equal to 3W. And H is equal to 50 over 3W squared. So we're just going to make those substitutions down in here in our cost function that we are trying to minimize. So 20 times W and then L is 3W. Plus 12 times H is 50 over 3W squared. L is 3W plus 12 times W, which we already have, and then H, which is 50 over 3W squared. Now we will simplify, take a derivative, and it'll be all great. So we have 60w squared plus, that's going to be 200. 12 divided by 3 is 4. Yeah, 400. W to the negative 2 is how I'm going to write him. Oops, wait. No, that won't be w to the negative 2. These 3's cancel. Those 3's cancel, so you end up with 12 times 50 is 600. Let me just rewrite this. 600w over w squared, because that's going to simplify a tiny bit. Plus, over here, 12 divided by 3 is 4. 4 times 50 is 200. So we have 200w over w squared. One of those w's cancels, so you have 600 over w plus 200 over w. These are like terms. They can be combined together. So you have 800 over w. And that can be rewritten, I know it's a lot, but this can be rewritten as 800 w to the negative 1. We are good to take the derivative now. So we have 120 w minus 800 w to the negative 2, setting this equal to 0. 120 w minus 800 over w squared equal to 0. Common denominator time, so multiplying by w squared over w squared. 120 w cubed, because there's 3 w's at this point, minus 800 over w squared equal to 0. If you set the denominator equal to 0, you get w equal to 0. That doesn't make sense. Clearly, your box can't have a 0 width. So the only other option is 120 w cubed minus 800 equal to 0. So this comes down to w cubed equals 800 over 120. So I get w cubed equals 20/3, which means w is equal to the cubed root of 20/3. We do need to verify this. To verify, taking another derivative, second derivative, you're getting 120 minus, oh, this will actually be plus, right? Plus 1600 w to the negative 3. You're plugging in this value here. So it's 120 plus 1600 cubed root of 20 over 3. And here's the thing, I don't need to actually plug this in to know it's positive. You have a positive plus a positive times a positive. This is clearly going to be positive. Positive would mean you're concave up, which means you have a minimum, which was what we were looking for. So we know that that works. So now it's just a matter of gathering the rest of the answer. So w is equal to the cubed root of 20 over 3. The length is 3 times w, right? That's from the right here. So 3 times the cubed root of 20 over 3. The height is equal to 50 over 3w squared. I'm getting that from right here. So 50 over 3 times cubed root of 20 over 3 squared. It's going to be nasty to put into your calculator. You do have to round this one to 2 decimal places. So when it all comes down to it, you're going to get w is approximately 1.88 feet. You're going to get that length is approximately 5.65 feet, and that the height is approximately 4.71 feet. And something you could do to kind of verify this, you could go back and make sure that the volume equals 50 feet. So if you multiply these numbers together, 1.88 times 5.65 times 4.71, you get 50.03, which is I mean, we know that these numbers are rounded, so that is close enough to 50 for me to say, okay, those numbers at least make sense in the context of this problem. So that was the long one. That was the hard one. But there it is. That is the entire review, and it only took me, oh my gosh, almost 3 hours. Thank you for the one of you that stuck around for the entire time. I am going to upload this. Do you have any questions about anything on here before I get going and let you enjoy the rest of your evening? Good, good. I'm glad that you understand them better. That's all I hope for. I'm glad it was helpful. So if you do end up having any questions, just feel free to send me an email. Otherwise, have a good weekend.